Hello, son. I'm happy to see you again. On the previous video of this series, we did our typer. So now we have an interpreter, we have a typer, but we don't have a syntax. So today we're going to be doing a syntax. But before, please don't forget to like, subscribe, enable the notification bell, share with your friends, maybe your family, maybe your mother will like to see a camel on YouTube. So let's begin. Today we're going to be using two tools. They're called sedlex, which is our lexer, and Menhir, which is our parser itself. And together, both you can call them the parser, but yeah, it's bad naming. The syntax that we are going to be writing a parser for is the one described here below. So like X of a type, C of a type, and the Lambda, which is an abstraction, and also an application. For this, we have first we are going to set up the tools because we are going to have some problems. Especially this one is a little bit trickier because when doing parsers, the problem is mostly related to infix operators because you need to define precedence, prefix operators because sometimes it doesn't work well, and juxtaposition, which is essentially this stuff. Like you have one and the other on the same side, like one on the side of the other. This stuff. E1 to E2. So the first step is that we need to actually have our AST on a module itself. So yeah, our AST is expression here. You can see. We're going to be moving it to a module. Because OCaml is a cool language, we need to do this. We can do this. There is a problem. Type is not known, so we need to define type, like type.ml. And we can do this. And because it was already in a module, just not in its own file, I can just do this. And you can see it still works nicely. So let's begin by defining our parser. Our parser, it's going to be something like this. And we need to use Menhir with June, you have a special stanza, which is this stuff. Now you can see errors are already happening. Like June added using Menhir, the version. I'm going to move this to here because it's cuter. And we need to define our parser. First, when defining a grammar, essentially you would want to define your tokens. Your tokens are the output of the lexer, right? So instead of you having a string, you have a sequence of tokens, which is like a string of tokens. And here we have some things. We have an ident. An ident is essentially a parameter or a variable, as you can see here, or here. You have two cases. We also have constants because we have integers. We then need parens, like L parens and R parens, so like left and right parens, like so. You also need a lambda, so like token of lambda. And because we have types, we need not only the lambda, not only idents, we also need a colon to separate the types. And we need a dot, so to separate the parameter from the expression. And I think that's it. Hopefully that's it. We're going to find out later. Oh, right. You also need to be able to declare the types. So for this, you need the arrow, like token arrow. And I feel like that's it. Hopefully that's it. One important thing here is that not only you need an ident, you also need to note the content of the ident, because you can imagine anything can be an ident. So A, B, C, and D, E, F are both idents, but you need to know which one. So we do something like this. And that means that inside of this ident, we have a string. Same for integers, because we need to know which number we are defining. And now that we have this, we can, it's talking that no start symbol has been declared. That's because we don't have like a start symbol. A start symbol is, you can think about it as the entry point for our parser. Here it's going to be something like expression, option, and expression OPT, something like this. Why it's an option? It's because let's say you pass an empty string. Yeah, it's an option. And we actually need something else on this topic of, we need actually a named token, end of file token, because we need to know when the stream of tokens ends. So the trick here is always something like you define an expression, and I'm going to be using the new syntax of Menhir. I find it cute, which is, let's think about it as something like this, and then you can go to your expression here, and it's an int, so you can create your ist by doing int of I. That's going to fail because it's not defined, but you also need to open it. I think it's like this. So open of expression. And here we need to define expression opt, which is our entry point. And here entry point is essentially a wrapper for expression, but it may be like nothing. So I have some examples there, which is EOF, and then here we go with none. And otherwise, it's just like an expression followed by EOF, and that's sum of E. So that's our entry point. You can see that this is recursive in both senses, always recursive. So you can go from here to here and vice versa. So yeah, it's saying that it does not know the tokens and etc. First thing, let's define our terminals. You can see that here I already did a case, but let's go with terminal. I'm going to be using two different declaration operators. This one is just like an alias, so there is no difference between doing this terminal. Like this is exactly the same stuff as before. It's just like sugar for it. And we also need to handle ident, so I of ident, and here it's going to be a variable of I. So now we have our base tokens, like our terminals. As soon as it hits here, it stops consuming the tokens. Menhir is an LR parser. I don't properly understand LR parsers, and I don't understand parsers at all. So here we're going to be doing a bad parser. And after terminal, we need to have abstraction. Abstraction is simple. I can define it abstraction as, let's go back, and we can see that abstraction may be a lambda. So it needs to be a lambda, followed by an ident, which is the param, a colon, then a type. Here we don't have types yet, so I'm going to declare this, and this is not going to build. And then an expression itself, so E of expression. And that's how we define an abstraction. So we have here abstraction, which is like param equals P, and we have param type, which is equals T. And we also have the body, which is an expression. So something like this. Let's focus here. So here you have an abstraction. There is some problems related to it, but let's define abstraction. It's going to fail because it does not have a type. So here this is not defined yet. Let's define it. So our types are simple. They may be int or not int. So I'm going to also define, like, that's going to be tricky. You're going to notice why. I'm also going to define another entry point that's useful for debugging, which is like a type of type. And here we're going to have a type. So our type is something like, it may be a constraint, but here we don't have full constraints, we just have integers. So you can say I of ident. And the trick is that you need to handle this ident. If it is an int, like so, you just say, oh, that's nice, that's a t int, great. Otherwise, we just raise an exception. I'm going to raise, I don't know, I'm going to go fail it, invalid type. So first, now this is defined, it's still complaining about the OPT1. You can do something like this and go with EOF none and expression of EOF, oh, it's t of type actually, and then go with sum of t. And now cannot be a start symbol and inline. Sure. So now you have your basics of your grammar, like we have abstractions. It's only missing the hard part. The hard part is essentially application, because application is like this. You can see that this is recursive. Abstraction is already recursive, like it goes a lambda and then it ends on expression. But expression also has an abstraction, so you can see that. Maybe you can see more easily like this. It's actually missing a dot, not that I noticed. So it's already recursive, but it's a good kind of recursive. Menhir can handle it. If I try to make application is just one expression the other side of the other. I'm going to try it. So like e1 equals expression, e2 equals expression. And if I try application of funct, which is e1, I'm going to move this to application, like so. And we can go here, e1 and body and argument is actually e2, I think. So like here, like this. You can see that something weird is going on. First, it's warning about us about something. You should not treat this as a warning. This is an error. That essentially means that you have some weird stuff going on your grammar. You don't want to ever have this. So why is this happening? Because you can see that there is some problems here. What happens is you can do an expression. Let's say an expression. I'm going to copy a lambda from, because I don't have lambda on my keyboard. Okay, I'm not. I didn't do APL enough on my life. So you have something like this, right? And well, this could be like any type. Let's say an integer, and it returns x. So this is a function from integer to integer, and you can apply it by doing something like this. But remember, right now we are not handling the parents. So this is a function, and you could try to apply it like this. But this is weird, because it could be this, right? It could be this, makes sense, which is identical. It could also be this. So we need to define the precedence, and we need to define actual parents. To define the precedence, it's a little bit tricky on LR parsers. You need to go, or like the way that I do it, and I don't know what I'm doing. I don't know what I'm doing. Okay, is to, instead of defining it like this, actually move terminal to subexpression. And subexpression is the expressions that can be accepted as an argument without having any ambiguity. So like terminal, if you have, let's say, a function, where's my function? Here. If you have a function like this, and you have x, so first expression on the left, you can easily put this. That's valid. You know it's applying with an integer abc. You know it's applying with abc, and the same is true for, like, you cannot apply it using an abstraction or another application, because if you try like 1 and 2, is it this? So 1 applies to 2, which is invalid, or is it actually, let's say ABC applied to 2, which may be valid, or is it actually this? Normally, that's the precedent stuff. We want left precedent, so left first. So here is this parent. To define it, we go and define something like terminal. And here we define our parents, which is like L parents, and it could be an expression. It could be any expression. So here you could essentially have this. And if you added parents, we could easily just accept this, right? That's not a problem. I could easily accept it. Not a problem at all. So we do our parents, and here it's going to just be E, right? Because we just defined it a precedence. And then we need to define, like, first, if I go this, you can still see there is a problem. And then on application, which is where the trick happens, application itself actually depends on subexpression. Oh, I could yeah, I could go like this, subexpression. And oh wait, sorry, wrong place. Subexpression. And here you can remove this. So this is still weird, but here we can then do application. Application, isn't it? Oh, it needs to be something like this. And now it's still going, but we still need to do something, which is like sub-expression. And now there is no error. That's great. Why there is no error? Because essentially, think about the sequence of tokens that you may have when you have ambiguity. Here we go to abstraction, and abstraction is never ambiguous. It's always an abstraction. But application may be ambiguous. So what happens is you go to application, and if it is a sub-expression, like if it is this, so a terminal or an expression with parents, we know that's just it. And the trick here lies that the recursion itself is defining like this. So on the left side of an application, it may be a terminal or a parent, like an expression with parents, or it may be also another application. So because sub-expression is terminal or expression with parents, and application itself is a sub-expression or an application. So here you have your precedence. It goes to the left, right? So it's always going to the left. We are going to have a case which is also right. It always goes to the right, which is for type, because you can see that Menhir is upset with us because we don't have like an arrow token. So we are not using it. We need to use it. That's the type arrow here. So this. To define it, also not hard. Same trick. I'm going to be applying the same trick. So like subtype. I'm going to be a bit lazy here, so I'm sorry. I'm sorry. So I go here, and here we also have parents, right? And it could be type and our parents, and this is just the. So what we need to do here is, because we just have the arrow, you can think about this as or let arrow. It could be any subtype, sure, or it could be a T1, which is a subtype, or followed by an arrow and another type. So like a T2, which is a type. And here it's going to be arrow. I don't know how I defined it this on type. So this was perm type and body type. Sure. So arrow, which is perm type T1, body type T2. I'm going to actually drop this line. Oh, it's the arrow, not arrow. Did you mean tint? Isn't it the type? Oh, I don't have type. I need to open type. Open type. Let's define it like so. And now our parser is mostly done. You can see that the precedence is defined by which side has the sub expression, right? So here the sub is on the left, here the sub is on the right. And if the sub is on the right, it's left precedence. If the sub is on the left, it's left precedence. Or in the other way, you can see on which side the recursion happens. So is the recursion happening on the left side? Yes. Is the recursion happening on the right side? Yes. Because if it is right precedence, the recursion is going to happen on the right side. If it is left precedence, the recursion is gonna happen on the left side. So that's simple. And now we have juxtaposition. When you have juxtaposition, you can think about the space as a token itself. Here we don't have space as tokens. That's great. That's a good practice. But you can think about, oh, this space is like an infix operator, right? So it's essentially saying this applies to this. It's a virtual infix operator, but well, now we have our grammar, and Menhir can generate it for us, but we need to define our lexer before using it. To define our lexer, I'm going to also create another module. The lexer, we are going to be using setlex as mentioned. So for setlex, and we're going to be using UTF-8. So open setlexing.utf-8. I think I forgot something. Yeah, I probably did. I need to enable, first there is a setlex.ppx. and also setlex is a library. We're going to need menhir lib, and also setlex itself. So now it's right, I think. Maybe I need to restart the Lambda server. Yeah, now it's right, but we are not doing anything with it. To make it useful, first we need to define some regular expressions. So let's define what is a white space to us. A white space to us is a setlex dot hashexp regular expression of one or more. I think yeah, it's one or more. So plus, right? Let me open setlex docs. I think star is zero or more, and plus is like, I don't know why GitHub it took so long. So yeah, plus is one or more, and star is like zero or more. So we can define it as a white space token. Sure, but there is also a couple of other white space tokens, like new line. New line is right. Wait, isn't it? Is the formatting not right? I don't remember. Maybe it's like this. Yeah, seems so. So you can see that this is accepts a pattern. And besides of new line, we also have tabs, because some people use tabs. We should not judge them. And we then need some stuff like alpha tokens. So for these, you can define it using a range from A to Z. Also a number from 0 to 9. What else do we need? We need to define some tokens which are bad. Like Lambda is particularly bad. I don't know if that's going to work, but let's try. Setlex, where's exp? And we are going to define it here as a Lambda. Let me copy a Lambda because, sorry, I don't have, I need to have to buy a keyboard with a Lambda. And now we have a Lambda. So besides of this, what else do we need? We need alpha, we need ident. Ident is a pain in the ass, because you need to first define that it can be any alpha, but it's not only one or more alpha, right? It's actually one or more. It's an alpha. It needs to start with an alpha, and then it needs to be followed by a star, so which is an alpha or a number, I think. And also I want to support underscore for, yep. So we support snake case, but we don't support camel case, because it's only lowercase lower. So I'm going to make lower alpha, make it easier, lower alpha. So what is this saying is essentially, it's first a character from A to Z, so a lower alpha, and then 0 or more lower alpha or number or underscore. So for example, this is valid ident, this is valid ident, ABC is valid ident, A123 is valid ident, 123 is not a valid ident, because we are also going to have our int, which starts, our int starts with, it's just a number, but it's actually one or more number, right? So that's an integer, and that's the basics, the basic regular expressions that we want. And then we need to do something that it's like a tokenizer. It accepts a buffer, and we do like match. Here we are using setlex ppx a lot, but well, it works. It's great. And why it's recursive? Because if it is a white space, we just ignore and go to the next token. So here we do tokenizer like this. And on the error, it's saying that setlex, the last branch must be a catch-all error case. That's true. So here I'm going to do a search false for now. I don't care about this branch. Stop formatting. And then we need more tokens, which is, this is our token list, by the way. So we need to open parser here. So our token list is something like ident. Let's do ident. Ident. And we can create an ident, but ident needs something like this. What is this lexme function doing is the matched part of the regular expression. So it matches an ident, When you call this, it's essentially reading all the matched section and moving in, copying to a new string. So this. By the way, this function is actually not pure because every pattern matching is actually changing the buffer, so it's not pure at all. We also need to define what an int, which is going to be exactly the same stuff. Oh, but yeah, I'm going to use string of int. Oh, int of string. This function, it could actually fail because int of string may raise an exception, but actually it doesn't because it's always like from 0 to 9, so it's not going to fail. We need to also define a lambda, which is just this, a colon. Colon is just colon, a dot, an arrow. An arrow is actually 2 tokens, so I can define it like so. I'm not going to be using Unicode arrow because I'm lazy, but we could be using it. And then we need to define left parens, up parens, right parens. And if it is an EOF, so if it's the end of the string, we do EOF. And I think that's about it. So if anything else happens, we just say it's invalid token. Let's create an invalid token. And here we do raise invalid token, like so. Great. And then we can like connect them together, and that's going to be enough for our parser. I think this is the worst video for me because I don't know anything about parsers. Actually, I'm quite bad with them. Here, like, I don't know why Menhir needs this by default, but I don't know a better way to do it. And to actually make the parser, I need to have some additional magic on the lexer. One of them is I call it a provider because it provides tokens for the parser itself. It's like a buffer, and then this, and then it goes like token, and it gets a token from the buffer. And we do start, stop, which is set lexing position of buffer. I'm going to explain why this needs to exist in a second, but I'm sorry. And then we do from string, which is f and string. So here we do from string. This from string is actually that's something interesting from OCaml. Like by default, idents are not recursive. So this from string is actually the one inside of setlexing, and I like it. I really like it. We go then provider, and here we use menhir convert, simplified, traditional to revised. Isn't it? Is it like so? Oh, I think I need to do this. I don't like sometimes OCaml format. Why in how is this like this? Let me do it in a different way, just to not look completely weird. And then you can do the lexer and the parser together. I'm going to actually put it here. So like from string parse expression, which is going to be lexer from string, and I need to pass a parser. It's expression opt. We can also define a parser parse type, which is type opt, and that should give us a valid parser. If I go here on June, yeah, I don't have it. Let's try to run it and see what happens for now. I don't think it's gonna happen. Yeah, it's still running the previous code. I'm going to comment it for a second. This is another cool feature of OCaml. Like you can have nested comments. And to try it, we can do parse expression x, and well, here we can put any expression. Let me try ABC first and see what happens. Oh, I don't know what happens. I need to do option get, and then I can print it using format printf of a, and I think so. And here it should be pp. We don't have pp for expression. Let's add pp for expression. No, not a problem to have pp for expression. Oh, I need to be building, otherwise it does not update. pp expression, and here I do x, and that should be it. I'm going to be adding an alias here on June. So June rule alias, I'm going to call it run to true, and on the dependency list is to true length.exe, and the action is just run to true length.exe. This is great because then I can just run it as run to true. Yeah, that's right. So our variable is right. I actually want to clean it. Show path equals false, isn't it? Hey, it's with path. So variable is right. Let's try applying a function, which is like abc f abc. That's also right. Let's try to applying again. So first it should apply f to abc. Yeah, that's also right. Nice, nice, nice. What else is missing? We need to try abstraction. To try abstraction, I actually need to copy this. Abstraction may be failing. I had a problem in the past regarding to this. So here it should be like int of x. Let's see. Yeah, invalid token. I think it failed on the lambda. It never entered the lambda. Let me try it. Lambda. Print in line lambda. Yeah, as you can see, it's not working. So in the past, what I did is manually matching any token. I'm not sure if that's a bug in the ppx or something like this. Let me buff lambda. Then it's lambda. Else is raise invalid token, and so this is never going to happen anymore. And we can remove that, and now I don't have this. So like this, and now it works. So it's probably a bug. I'm sorry. But you can check for each character individually when you need it. It's a pain. We can probably improve on it, but no. So here you can see that it's matching. So it's a parameter from x, type t int, and a body of variable x. We can then infer it. So I'm going to actually make a function called print expression, just AST. And the print expression is actually going to do parse expression, AST, option.get, and then format fprintf of a and so pp expression. Isn't it right? Oh, it's printf only. And here I can do then print expression, remove it. Yep, that's right. We can also print the infer type by doing not AST code. So we do code, and here parse expression, code, option.get, infer, it's simple. Do I have infer here? How is it defined? Oh, interp. What is my typer? Oh, infer.infer, isn't it? And env.empty. Infer, env.empty. What is wrong here? So this returns expression. Oh, no, it's not env, it's context. Sorry, I'm playing too much with the other project. And same stuff here. We do printf a and type.pp type, like so. And we can try print type. Now we can see that it inferred the right type. Let's try something else. Let's try to apply it. So the one, it also inferred the right type. My camera died. Great. Let me fix my camera. It happens sometimes. But yeah, my camera is now back. Print type, it's okay. Now it's done. What else can we try with now that we have a parser? We can try doing int. So that's an identity function for something like for the previous function. So we can go here and say int, and then .x, like so. And yes, that works. So, and you can also do this. You can see that the inference is working. You can play with the syntax. And the great thing about this is that it's quite simple to define. The error messages are not great. Let's say I do this like this. It's essentially saying an error happened. But error messages are one of the hardest part in parsing and actually typing. So having proper error message is hard. And I don't want to enter in details right now, but Menhir, the parser generator, has like the needed tools to do parser recovery and good error messages. You just need to implement. Uh, I don't know how to do it. I need to study it. But if I do in the future, expect to see a video here. Well, yeah, that was about it for today. We have a typer, we have a parser. We actually have a Turing complete programming language if we hack some stuff. Let's try. That was famous last words. Let's not try anything else, otherwise the video is going to be an hour long. Please don't forget to like, subscribe, share with your friends, enable the notification bell, post on Twitter, follow me on Twitter. My Twitter is nice. Not nice, but anyway, follow me on Twitter. Uh, yeah, that was it. Have a nice day. Have a nice week. Sleep well. Bye.